Welcome back, everybody. So for a while now, one of the things we've been thinking about has been adding up information on one-dimensional things. If we have some curve, either in the plane, like we do here in the picture, or maybe that curve is floating around 3 space. If we want to do a line integral over a curve like this, the first step that we need to take is to parameterize the curve. Well, very shortly, we're going to be thinking about one dimension higher and thinking about parameterizing surfaces in order to add up information about a surface, a two-dimensional surface floating around in space. And today, we're going to get a feel for what a parameterization of a surface looks like and how to find one. And what's nice is that they're completely analogous to parameterizations of curves. Where I'd like to start today is to start by kind of gathering our thoughts about that context, thinking about parameterizations of curves. And so to start off, well, let's start with the maybe most basic question we can ask. What sort of mathematical object is a parameterization of a curve like this one? What sort of mathematical thing is it? Well, as a step in the right direction, we might recall that normally we give these things the name r hat, but that doesn't really answer the question. What kind of mathematical object is r hat? Well, it's a vector function. Right, this is r hat is a vector function. If we're in the plane here, it's got two components. And each of these components are going to be functions of one variable. Right, we often call it t, but that might take a different form depending on what curve. We might have theta as our parameter, we might have y as our parameter, etc. But it's a vector function. That's its most basic form, and a domain for that vector function. Right, if we have one parameter, then we just need a range of t values that we're thinking about. And so, by the way, this one variable that we use to parameterize our curve, that's directly coming from the fact that our curve is one-dimensional. Okay, so this is what a parameterization is, just in terms of ground floor, what sort of mathematical object is it, but what sort of job does our r hat have in terms of our curve? What does r hat do? Well, the answer to that is our parameterization's job is to, through the different values of our parameter that we plug in, to go through and output each and every point along our curve. That's our parameterization's job. Right, we want to go through and get each and every point on our curve so that, thinking about line integrals, we can then go through and add up our function information along those points. All right, so that's what a parameterization is and what its job is. How do we actually find a parameterization? Well, the way that we've been thinking about this is that we want to describe our curve just in a chosen set of coordinates. And once we have that description, we can use that to find the x and y coordinates or the x, y, z coordinates, if our curve is in 3 space. And so, for example, right, with our situation up here, this curve is a nice chunk of a circle. So we could think, either in polar if we want, or we could just say whatever and use rectangular coordinates anyway. In polar, it's like our description would be r equals 2, and thetas we're going to want to use are from 0 to pi, right, in order to move us the correct direction. And right, so that would be our polar description. Right, in terms of rectangular, the observation is, hey, our curve is actually a function of y. Sorry, I said that wrong. Curve is a function of x, right? For each x, there's a unique point on our curve. There's a unique y value. And so we can use x as our parameter, and we can just take our equation, solve it for y in terms of x. And I guess here we get plus or minus square root, and we want the positive square root 4 minus x squared. All right, and here we'd want to move x from positive 2 to negative 2 in order to move the correct direction there, right? And we could take, our x and our y, and we could just pop them in for our x and our y coordinates. With polar, we need to do a little translating first, right? Translate to get our x and y using what those are in polar, right? R cosine theta and r sine theta, right? And we'd use the fact that r equals 2, and we'd be good to go. We'd have another parameterization that we could use for our curve. And so this is how we've been thinking about finding a parameterization, getting a description, and then using that to find our coordinates for our parameterization. The nice thing about parameterizations of a surface is that we have the exact same idea as we do for curves. We just have one dimension higher. All right, parameterization of a surface is still a vector function. It's still a vector function, but now, because a surface is two-dimensional, one parameter t is not going to cut it. If we want to describe this two-dimensional surface floating around in space, we need to use two parameters. So our parameterization is going to be in terms of two variables. And just to name them something, we normally I call them u and v. That might be x and y, it might be r and theta, right, depending on our particular context. But just as a general name, u and v are what we name them. So our parameterization is in terms of two variables. And again, we need to give some sort of domain for our function, and that's going to be a two-dimensional domain telling us what values for u and v we're thinking about. So it's the same sort of object, just with one more variable. Maybe just for our note's sake, let me mention here, since a surface is two-dimensional, that's why we need two variables. This parameterization, it's the same sort of object, and it has the exact same job as it did before. Our parameterization is just designed to go through and output each and every point along our surface. So maybe this point right here on our surface, that's r hat when we plug in, I don't know, 2, 3 into our parameterization. And maybe this point over here, that's what we get when we plug in, I don't know, -1 pi into our parameterization variables u and v. We get that point, right? And we get this point when we plug in some other values for u and v. And if we go through this whole two-dimensional domain, we output each and every point on this surface. So it has the same job of outputting all of our points, and in fact, we have the same way to think about finding these parameterizations in terms of describing, in this case, our surface in a set of coordinates, and then using that to find, in this case, it'll be x, y, and z always, because our surface lives in 3 space. All right, so each point here on our surface is a x, y, z point that we need to describe and get through our parameterization. Okay, so what I'd like to do now is look at a particular example. So here we have an ice cream cone. A little chunk of the cone, z equals root x squared plus y squared, at and below z equals 1. So in other words, starting from the vertex of the cone and moving up to z equals 1, this is our little ice cream cone that we're thinking about. And what I'd like to do is just dive in and give you a chance to try and find 2 different parameterizations for this cone. And these 2 different parameterizations are going to come from describing this thing in 2 sets of coordinates. And we can see way 1 right here. We can think of this and describe it using rectangular coordinates and use that description to find our parameterization. Way 2, we could also think about describing this in cylindrical coordinates. We could also technically try and describe this in spherical coordinates and get our parameterization. That turns out to be somewhat ugly. And so let's not worry about that. Let's just think about these 2 ways, thinking in terms of rectangular and cylindrical, in order to describe this cone and then come up with our x, y, and z for our parameterization. Pause the video and dive in and see if you can describe this surface and come up with these parameterizations. Then we'll talk about them in just a sec. Okay, so thinking in terms of rectangular, the observation here is that, hey, our surface is actually a graph. This is given as a graph of a function of x and y. Right? Our equation is z equals something in terms of x and y. And so what this is telling us is that we can actually use these variables of the function x and y as our parameters. So we're just going to, in terms of x, y, and z, we're going to leave x and y alone. Those are going to be our parameters. And this little cloud of stuff in terms of x and y, we're just going to plop that in where we see z, and right away we have a good to go vector function that's going to work as our parameterization. The only thing we need to answer is what's our domain for our vector function, right? What x's and y's does our cone use? Now, to think about where these would come from, right, well, let's imagine for a sec that we were doing a triple integral over not just the outside of the ice cream cone, but maybe the inside as well. Maybe we had this leveled off with, runny ice cream way up to the top. Well, if we wanted to do our limits of integration, right? If we wanted to move z first, we'd say, okay, start z at the cone and then move it to the top, the z equals 1 plane. And now if we wanted to then figure out and answer the question, okay, well, what x, y points do we want to do this for? That question is, what's the shadow of our cone? And that's what is really going to tell us what x's and y's we want to use as well. We can think of this parameterization as telling us, okay, go to the point x, y, and then what does our z coordinate have to be there? It has to be exactly z equals root x squared plus y squared. So that the point we get lives on our cone. And so we really want to figure out what is the shadow of our cone to figure out the x's and y's we need. And so here, our shadow, the outer rim of our shadow at least, comes from the top side here of our cone, and that's where we cut things off with the plane z equals 1. And so that's how we're going to find the outer rim of our shadow. Just take the trace, the z equals 1 trace of our cone. If we combine those, we see that we get the unit circle. Again, just as the outer rim of our parameterization. Right, but looking at our picture up here, right, the shadow of our cone is actually the filled-in disk. And so we don't just want this outer rim, we want all the insides as well, the guts of it. If we're going to, through our parameterization, trace out our two-dimensional surface, we need this two-dimensional domain. All right, and so real quick way to describe that, if we'd like, is just x squared plus y squared is less than or equal to 1. That's a fine description of our parameterization domain. If we wanted to set this up more in the language of limits of integration, we'd say, okay, well, let's move y from the bottom half of the circle up to the top. And what x's do we do this for? Well, from -1 to 1. And so this is one complete parameterization. We have our vector function and we have our two-dimensional domain for our parameters. So now let's think about getting our parameterization using cylindrical. And here again, let's think along the lines of how this would look, if we were doing a triple integral, how we would get our limits of integration. Well, for cylindrical, right, we'd pick a variable to move in rectangular first. And so actually we have the first step being the same, right? If we had our ice cream cone and the filled-in ice cream for a triple integral, we'd want to move z, and we want to start it on the cone and move it up to the plane and stop there. But here, for our surface parameterization, we don't want to start at the cone and then move up to the plane. We just want the cone, and so we just are going to have z equals root x squared plus y squared. And in terms of cylindrical, x squared plus y squared is r squared, and that simplifies down to z equals r. All right, but then the next question again is still the same. What points in the plane do we do this for? In other words, what's the shadow of our cone? Right, and we still have the exact same shadow as we did above. We have the unit circle filled in. Here to describe this, thinking in terms of cylindrical coordinates, so polar coordinates in the plane. We're using angles from 0 up to 2 pi. And for each one of these angles, we're letting r start at 0, and we want to let it move out to 1. And if we do that all the way around, we will indeed trace out our whole unit disk. All right. And so here, our surface Z is given in terms of R. And our shadow, we have a nice description in terms of R and theta. And again, what this is suggesting to us is when cylindrical, we want to use R and theta as our parameters and get X, Y, and Z in terms of them. Maybe I'll stop there. And so we need to get X, Y, and Z for our parameterization. Our Z component, that just comes from our equation above. Right, Z equals R from the equation of our cone. X and Y, we just need to translate these using our polar translation equations. That X is R cosine theta and Y is R sine theta, right? That is what writes X and Y, these rectangular coordinates, in terms of R and theta. And so just popping all three of those in, we get our parameterization vector function telling us our X, Y, and Z for a chosen R and theta. And then down here, we have our two-dimensional region for our parameters. And this is just coming from our description of the shadow. And again, let me mention that it is definitely possible to use spherical, to think in terms of spherical description of our cone to find our parameterization. But it is a little bit messier than these two. But it would be a great exercise if you wanted to try that out and see if you could describe the cone in spherical and then use that to find the X, Y, and Z components of a parameterization, as well as the domain for your parameters. All right, well, that's it for today. Next time, we'll think about adding up information over these surfaces that we'll have parameterized. But for today, if you have any questions, post those to Piazza, and I'll see you next time.